Now next comes the condition for existence of conjugate lines. Now when do we say the two lines are conjugate is the biggest question of the topic. So let's see the condition for existence of conjugate lines. Suppose I take the two lines L1x plus M1y plus N1 L2 x plus M2y plus N2 are the two lines, then these two lines are said to be conjugate lines with respect to the circle S equal to 0 if I have the condition r squared times L1 L2 plus M1 M2 is equal to L1G plus M1F minus N1 L2G plus M2F minus N2. Where I have R as root of G squared plus F squared minus C, which is radius of circle. So the condition here is that for two lines to be conjugate with respect to the circle S equal to 0, R squared into this must be equal to this times this, where L1, M1 and N1 and L2, M2, N2 are extracted, and R, which is given by the formula root of G squared plus F squared minus C, is the radius of circle which we find using G, F and C extracted from the general equation of circle. The condition for existence of two lines to be conjugate is this. The next is about inverse points. When do we say that the 2 points are inverse points is the biggest question. That is, if suppose I have the circle S equal to 0, then P and Q are said to be inverse points for the circle S equal to 0 if my first condition is that C, P, Q are collinear, and my second condition is that P and Q are on the same side of C, on the same side of C, where C is center of circle, and the third condition is that CP dot CQ is R squared, that is CP times of CQ is R squared, where R is radius of circle. So let's take the diagram and see how we can understand the inverse points. Say for example, I have a circle S equals 0 and I have the center of circle out here. Now if suppose I have 2 points P and Q such that they are collinear, that is I have P here, Q here and my point P here, then in this case the radius of the circle is R. Then if P and Q are on the same side of C, then CP dot CQ equal to R squared is the condition which makes us define the inverse points. So under these three conditions, we say that the points P and Q are inverse points with respect to the circle S equal to 0 if C, P, Q are collinear, P and Q are on the same side of C center, and CP dot CQ is R squared. Is how we define the inverse points with respect to the circle S equal to 0. Now let's see the inverse points for standard form of circle. That is, if I take the circle in the standard form as x squared plus y square equal to r square, then PQ are said to be inverse points for this if and only if Q is the point of intersection, if Q is the point of intersection of polar of P and CP. So the point of intersection of CP and the polar of P will give us the 2 points to be inverse points for the standard form of circle. So let's see with the diagram. Suppose I have a circle x square plus y square equals r square. Now for this standard circle, the center being origin, I take the center C and I take the point P somewhere here. Then if I say that the polar of P lies here, and then the say CP intersects here, then this is the polar of P and this is the line joining CP, and then the point of intersection of CP and polar of P, if this is Q, then we say these 2 points are inverse points. So under the case, this point Q becomes an inverse point with P, is how we understand the concept. PQ are inverse points if and only if Q is the point of intersection of polar of P and CP, is how we understand the inverse points connected with standard form of circle. Now say, for example, I have a circle S equal to 0 in its general form. Now let me take a point, let me take the center of the circle to be C. Now I have a point P out here whose inverse point I would like to find. So what would be the inverse point of P with respect to the circle S equal to 0? So here let me draw the polar of P somewhere passing through here. So this is polar of P. Now here the inverse point of P is the point which is the foot of perpendicular from center to the polar of P. That is, if this is the polar of P and this is the center of circle, then inverse point of P is the foot of perpendicular, which is Q. So Q is the inverse point of P. So when I just extend out here, I get this to be collinear, as I can clearly see that C, P and Q are collinear, and in this case Q is, which is the foot of perpendicular from center of circle C to polar of P, is nothing but is the inverse point of P. So we understand Q, which is the foot of perpendicular from center of circle to the polar of P, is nothing but the inverse point of P, or inverse point of Q is P, vice versa, is how we understand the inverse point connected with foot of perpendicular of from the polar. Now let's see one of the example problem through which we understand the concept of finding the inverse point through a better procedure. So if I have a problem, it says find the inverse point of minus 2, 3 with respect to the circle x square plus y square minus 4x minus 6y plus 9 equal to 0 is the question out here. So here I clearly have the circle S equals x square plus y square minus 4x minus 6y plus 9 equal to 0. And one of the inverse point is given to be, say I take as P, which is minus t minus 2, 3. Now the question is to find the other inverse point. So for this, let me take the diagram. Now here, the center of C, which is center of S, which is denoted by C, is given by minus G minus F, that is 2, 3, as derived from here. Now if I take a circle whose center is 2, 3 and I have a point P which is minus 2, 3, then we know that the polar of P is somewhere passing here, and I have this out here. So we know that Q is the foot of perpendicular from C, which is exactly out here. So Q is the point of intersection of polar of P and CP. If CP is the line, if this is the polar, then polar and the line CP intersect at Q, which gives us the inverse point. So it is essential that we find the polar of P and we find the equation of CP and solve them through elimination method to get the point of intersection Q. So let's see how we can find each of them. So initially, polar of P minus 2, 3 with respect to the circle S equal to 0 is S1 equal to 0 using the formula. So S1 equal to 0 implies x1 plus y1, half of this, which is minus 2 of x plus x1, half of this minus 3 y plus y1 plus 9 equal to 0 is what we get. Now simplifying this more further, we get this to be minus 2x, which is minus 4x, and 3y minus 3y, which get cancelled to give 0, and 4 minus 9 plus 9 gives me plus 4 equal to 0, that is x equals 1. Now this is the equation of the polar P. This is the line x equal to 1. So equation of line polar is x equal to 1. So is what we get. Now next, it is important that I find equation of CP. So equation of polar P is x equal to 1, which I take as equation 1. Now next is equation of CP. So this is polar of P, which is minus 2, 3. Next, to find equation of CP, I consider C, which is 2, 3, and P, which is minus 2, 3. Therefore, if I take this as x1, y1, and this as x2, y2, then I have y minus y1 is equal to, using the 2-point form of line, is y2 minus y1 by x2 minus x1 of x minus x1. So this on simplification gives y minus 3 equals 0 times x minus 2. That implies y equal to 3. Therefore, y equal to 3 is equation 2, which I obtained from finding the equation of line CP using the 2-point form, using the formula y minus y1 equals y2 minus y1 by x2 minus x1 times x minus x1. Substituting each of them, I get this to be this. Now solving these two equations, I get, therefore, Q is equal to 1, 3, which is the point of intersection of 1 and 2. So the point of intersection of 1 and 2 is nothing but 1, 3, which I have obtained, and this is nothing but the inverse point. Also, that implies Q equal to 1, 3 is the inverse point of P with respect to the circle S equals 0, is how we understand the finding of the inverse point of the circle with respect to the other point. So, finding of inverse points requires solving of two equations to find the point of intersection of two lines by elimination method. Now let's see how the equation of chord can be connected with the middle point, and hence finding the equation of the chord through its middle point, the given midpoint. So for example, I have a circle S equals 0, and I have the center of circle here, and I have a chord AB, or I have a secant through which I get the chord for the circle in this way. It intersects the circle at AB, and let me say this is the midpoint of the chord AB, and let the coordinates of the midpoint be x1, y1. So if M is the midpoint, is the midpoint of chord AB, that implies equation of secant AB or the chord AB or chord AB with respect to the middle point is S1 equals S11, is how we understand the concept of middle point connected with finding equation of chord. So equation of chord or the secant with respect to the midpoint x1, y1 is S1 equals S11, is how we understand the equation of chord through the middle point. Now that we have discussed about circles and the position of points and position of lines with respect to the circle, now let's come to the understanding of what happens if two circles have their relative positions changed. That is, if the two circles touch, or if the two circles intersect, or if the two circles are disjoint. So let's come with three cases and see identically on what are the different properties studied under these three cases. So initially, to come with case 1, case 2 and case 3, where the first case is intersecting circles touching circles and disjoint circles are the three cases which we have here. Now, as I see the intersecting circles, I see that the two circles are said to be intersecting if they are in this form. They are intersecting circles because they have some overlapping region in between. Therefore, these two are intersecting circles. Now, when I say touching circles, I have the two circles touching each other. This is how we understand. Or the possibility is that this can also touch inside, where this is called touching externally, and this is called touching internally. Because the two circles are touching inside each other, and here they're touching outside. So touching externally and touching internally. And disjoint circles are the circles which do not intersect. There is no overlapping region like here. They're just way apart. There's some space in between the two circles. So with these three cases, we study the different types of properties involved with this. Now, as I come with the relative positions of circles, now I connect with the tangents connected with these three types of circles. So let's see the tangents connected with the relative positions of circles with each of three cases. Now let's connect the relative positions of circles with the number of tangents which can be drawn for that position of circles. Now, as we have taken three different cases of circles which are possible when you take them in relative positions of combined circles, now let's see how the common tangents can be drawn. Now we know that a common tangent is a tangent which is a tangent to both the circles together. Suppose I have two circles which are like this, then this is a common tangent because this line is a tangent to the circle 1, and this line is also a tangent to the circle 2. So if a line is a tangent to both the circles at once or at the same time, that tangent is called a common tangent for both the circles. Now, as I see for these two circles being intersecting circles in case 1, if I draw a tangent here, and if I can possibly draw another tangent out here. So two tangents can be drawn, common tangents can be drawn for intersecting circles. Therefore, for intersecting circles, I can draw two common tangents is how I understand for intersecting circles. Now when I have touching circles, let's see how many common tangents can be drawn for touching circles. As I see for two cases of one being touching externally and the other being touching internally. So in this case, I have tangent 1 and only one tangent which can be drawn for these two. And also I have these. Therefore, as we see the two circles touching externally, I have totally 1, 2 and 3. So there are 3 tangents, common tangents, when the two circles touch externally. But in case of touching internally, there is only one common tangent which I have for the two circles touching internally. Now when the two circles are disjoint, let's see how many common tangents I can draw through this disjoint circles. I have 1, I have 2, I have 3, I have 4. So therefore, the totally T1, T2, T3, T4. So that is, there are 4 common tangents which I can draw for disjoint circles. Therefore, I understand that for case 1, where the two circles are intersecting, I have 2 common tangents which are these 2. For two circles touching externally, I have 3 common tangents which I have here, T1, T2, T3. For two circles touching internally, I have 1 common tangent which is this. For two circles which are disjoint, I have 4 common tangents, 1, 2, cross 3, cross 4. is how we understand the relative positions of circles connected with number of tangents. Now let's see the mathematical property for condition for disjoint circles. So that is, if the two circles are disjoint, then how do we identify for the disjointness through the mathematical equation or the formula? Suppose I have two circles with circle 1 being with center C1 and with the next second circle being with center C2. Then if the radius of this circle is R1 and the radius of this circle is R2, then I have the distance between C1 and C2. For the two circles to be disjoint, the condition is that the distance between C1 and C2 is always greater than sum of the radius. Is how we understand the condition for two circles to be disjoint. The distance between their centers is always greater than the sum of their radii, where R1 is the radius of this circle and R2 is the radius of this circle. Condition for disjointness of two circles is this greater than this. So next, let's see the condition for touching circles. As we know that there are two types of touching circles. One is touching externally and touching internally. So there are two different cases which arise with two different types of touching circles. So if I have the two cases of touching externally and this is touching internally, then with these two cases, let's see how we can derive for touching circles. Now when I clearly see that the two circles, say one with center C1 and other with center C2, and radius of this circle is R1 and the radius of this circle is R2, then clearly I see that the distance between their centers is nothing but sum of their radii, which is R1 and R2. So in order that these two circles touch, the condition is the distance between C1 and C2 must be equal to R1 plus R2. Is the condition for two circles to touch externally. Similarly, if I have two circles touching internally, the center of this circle is C1 and the center of this circle is C2 with radius R1 and R2, then clearly when I join these two, I see that the distance between C1 and C2 is R1 minus R2. This minus this gives me the distance between two centers. Therefore, the condition is this equals mod R1 minus R2, whichever is greater. The modulus comes because if the value is negative, we make it positive by putting the modulus. So this is the condition for internally touching circles and condition for externally touching circles. Now let's take the third case of intersecting circles. That is, if the two circles are intersecting, then I have this C1 and C2 and radius of this circle is R1 and radius of this circle is R2, then the distance between their centers is obviously less than the sum of the radii, as can be clearly seen here. Therefore, the condition for this is the distance between the two centers of the circle is always less than the sum of the radii of the two circles. If the distance between centers is greater than the sum of the radii, the two circles are disjoint. if the distance between the centers is less than sum of the radii, the two circles are intersecting circles. Now the next case is where the condition for one circle inside the other, that is, if I have a whole of the circle which is inside the other circle, say like this, with center C1 and center C2, then here I clearly see that the condition for one circle to be inside the other is the distance between the two centers is less than mod of R1 minus R2 is how we understand the condition for whole of the circle to be inside the other circle. The condition is this less than this is how we understand the condition for one circle inside the other circle. Now next is the concentric circles. We know that two circles are concentric if they have same center. That is, if I have a circle which is concentric with this, then that means they have same center. So let me say the center of the bigger circle is C1 and the center of the smaller circle is C2 with the respective radii being R1 and R2 respectively. Then for the two circles to be concentric, the distance between their centers is 0, or mathematically we say that the two centers coincide, or C1 and C2 coincide is how we understand the condition for concentric circles. Center of similitude. Now that we have discussed the common tangents for three types of possibilities of circles: touching, intersecting and disjoint. Now let's connect the center of similitude with those three cases of the circles. Now to bring back all the three cases out here, I have so these two are disjoint circles and these two are touching circles and these two are intersecting and these two are the intersecting circles. Now here I have these circles which are disjoint or non-intersecting. We know that we have four tangents which can be drawn for these types of disjoint circles. Now revisiting the common tangents concept, there are four common tangents which I can draw. One is this, and the other is this. And let me say the center of this circle is C1 and center of this circle is C2. Then when I join exactly, I see that there are 2 points of intersection of the pair of tangents. One is P and the other is Q. So when the pair of tangents intersect outside the two centers, this point is called the external center of similitude, and if the pair of tangents intersect between the centers, then that point of intersection is called internal center of similitude. So in this case, these two tangents, when they intersect at P, P is called external center of similitude, and Q is called internal center of similitude. Next, if I have the pair of tangents, we know that there are 3 pair of tangents which I can draw for this. 1, 2 and 3. If the center of this circle is C1 and this is C2, then if I join here, then there are 2 points of intersection. One is P and the other here is Q. So here Q is between the two centers C1 and C2. Q is called internal center of similitude and P is called external center of similitude. So in this case, P is external center of similitude and Q is internal center of similitude, as we can see the case here. Now similarly, if I draw the common tangents out here, the center of this circle and center of this circle pass through the point P, which is called external center of similitude. But in this case, there is no internal center of similitude because no tangents intersect between the centers of circles. Therefore, no internal center of similitude is how we understand the 3 cases of disjoint circles, touching circles and intersecting circles through the center of similitude. And also, as I see the second case, there is one more possibility that the 2 circles touch internally. So in case of the 2 circles touching internally, then in this case I have the tangent here, which is T, and therefore I have P, which is outside of centers P, C1 and C2. Therefore in this case P is external center of similitude, but there is no internal center of similitude when the 2 circles touch internally. There's only the external center of similitude, which is the point of contact of the tangent with the 2 circles. Now let's see how to find the center of similitude connected with the given problems, respective problems. Say for example, I have a problem which says find the number of common tangents which can be drawn for the circles x square plus y square minus 14x plus 6y plus 33 equal to 0, x square plus y square plus 30x minus 2y plus 1 equal to 0. So the initial part of the question is this, and also find the external and internal centers of similitude if they exist. Now this question is related to the center of similitude, but before that, the part 1 of the question is to find the number of common tangents which can be drawn for these 2 circles, and we know that the number of tangents depends on the relative positions of the 2 circles, whether they are intersecting, touching or disjoint. So let's see the relative position of these 2 circles before we find the internal and external centers of similitude. Now as I take the two circles, I have the first circle, which is x squared plus y squared minus 14x plus 6y plus 33 equals 0. And my second circle, which is s dash x squared plus y squared plus 30x minus 2y plus 1 equals 0. Now clearly the center of this circle, if I denote by C1, is minus g minus f, that is minus g and minus f, which is this. And the center of this circle, which is denoted by C2, is minus g 15, that is minus 15, and minus f, which is 1, extracted from gx, 2gx and 2fy. Now that we know the centers of each of the circles, now is the question in finding the radius of each of the circles. If suppose radius of this circle is r1, then this is root of g squared plus f squared minus c. So root of g squared plus f squared minus c is formula. And then I get this as 49 plus 9, which is 58 minus 33, is 40, 18 plus 17. So 58 minus 33, 30, 40, 18 plus 7, 25. So root 25 is 5. This is the radius of the first circle, R1. Similarly, if R2 is the radius of the second circle, then I have root of g squared plus f squared minus c, that is root 225, which is 15. So therefore I have the radius, the radii and the centers, through which I am going to find the relative positions of two circles, which in turn gives me the number of tangents. Now I find the distance between the two centers and connect with radius. So therefore, if I want to find the distance between two centers, then I use the distance formula, root of x2 minus x1 whole square plus y2 minus y1 whole square. Plus 7, which is 5, 22. $484 plus 16, which is root 500. That is, therefore C1 C2 distance is root 500, that is 10 root 5. So clearly I see that this is 10 root 5. And my R1, which is 5, and R2, which is 15, gives me R1 plus R2, which is 5 plus 15, which is 20. So clearly I see that R1 plus R2 is 5 plus 15, which is 20, which in turn is equal to root of 400. So clearly when I see equation 1 and equation 2, from 1 and 2, I see that root 500 is greater than root 400. That implies root 500, which is C1 C2, is greater than R1 plus R2. So as I see the relation with this greater than this implies the distance between the centers is greater than R1 plus R2. That is, this is possible only when the two circles are disjoint, because the distance between the centers is more than the sum of the radii. The two circles must be far apart, disjoint circles. So therefore, this implies the two circles are that implies the two circles are disjoint. Now when the circles are disjoint, let's see how many common tangents we can draw for the two disjoint circles. So let's take the two circles where the radius of this circle is 5 and the radius of this circle is 15, and this is given by C1 and C2, where the coordinates of C1 are 7 minus 3 and the coordinates of C2 which are minus 15 and 1. So this is the case of two circles which are disjoint in nature. Now as I can clearly see that there are four common tangents which I can draw, that is 1, 2, 3 and 4. So there are totally T1, T2, T3, T4. So four common tangents can be drawn for the given circles. So with the conclusion that there are four tangents which can be drawn for the given circles is part 1 of the question. Now next comes the part 2 of the question, which wants us to find the centers of similitude. Now we know that for these two disjoint circles there are two centers of similitude, one being this and one being this. So there are two centers of similitude, this being internal center of similitude and this being external center of similitude. So with these two centers of similitude, which you're going to find using the centers and the radii, is how we find the centers of similitude. To be continued. Now here, initially to find the point Q, that is the internal center of similitude. So in order to find Q, I utilize the points C1 and C2 and then see how we can do it with respect to the ratio. Now here the ratio is clearly R1 is to R2, that is 5 is to 15, which is 5 ones, 5 threes. So the ratio of R1 is to R2 is 1 is to 3. Now Q divides C1, C2 internally in the ratio 1 is to 3. So we have discussed in coordinate geometry that if a point divides internally in the ratio m is to n, then we have the formula m1x2 plus n1x2 by m plus n, and so on and so forth, through which you get this. Therefore, in order to find the coordinates of Q, I use the formula mx2 plus nx1 by m plus n. That is, this is x1 y1, x2 y2, and this is your m and this is your n. So using the formula mx2 plus nx1, mx2 plus nx1 by m plus n, and then my2 1 times of 1 plus ny1 by m plus n, which on simplification gives minus 15 plus 21, which is minus 15 plus 7 3 is 21 by 4, and 5 3 is 15 plus 1, 16 by 4, 2 2s, 2 3s, 4 1s, 4 4s, minus 3 by 2, comma 4. Therefore, the internal center of similitude Q is given by minus 3 by 2 and 4. The internal center of similitude is how we obtain with this. Now next comes on finding the external center of similitude, that is point P. Now next is to find the external center of similitude. I take the same ratio R1 is to R2, which is 1 is to 3, and Q divides, P divides the distance between centers C1 and C2 externally in the ratio 1 is to 3. Now we know that if a point divides externally, then we get the formula mx2 minus nx1 by m minus n. All the plus in between is replaced with minus for external point which we find. Therefore, in order to find P, it is nothing but mx1, where this is m and this is n. So mx2 1 times of minus 15 minus nx1, which is this, by m minus n. So all the plus is replaced with minus in the middle, because this is externally dividing in the ratio 1 is to 3. Similarly, my2, which is 1 times of 1 minus ny1 by m minus n is what we get. This on further simplification gives minus 15 minus 21 is 26 minus 36 by minus 2, and then 1 minus 15 by minus 2, which on further simplification gives minus cancelled, 2 1s, 2 18s, 2 1s, 2 7s, which is 18, 7. Therefore, point P is 18, 7, which is called the external center of similitude. So this is how we find the internal center of similitude and the external center of similitude for the given respective relative positions of circles, and identify the number of tangents through this example problem. Now let's take the concept of combined equation of pair of tangents. That is, say for example, I have a circle S equals 0. And for this circle, let me say P is an external point outside the circle with coordinates x1, y1. So for a point P outside the circle, that is for P is an external point of the circle, we know that there are two pairs of tangents which can be drawn for the circle. So we have two pairs of tangents, one pair of tangent, that is T1 and T2, which can be drawn from external point. So equation of these pairs of tangents is given by the formula equation of pair of tangents T1 and T2 from Px1 y1 with respect to the circle s equal to 0 is given by s1 square is equal to s times s11 is how we understand the equation of pair of tangents given by the formula s1 square equals s times s11. So equation of pairs of these two tangents together is given by this formula, the pair of tangents with their equation.